Welcome back to the Deep Dive. Today we're tackling a question that's, well, pretty huge.
Yeah.
Where did all the energy in the universe come from? We got the Big Bang, stars, galaxies, us.
Right. It all takes energy.
And one of the most basic laws of physics is that energy can't be created or destroyed.
Just transformed. Yeah.
So where did it all begin? What was the original source? I'm so curious to unpack this.
Me too. I'm really excited about this one. We've got some really fascinating ideas from our sources.
Yeah, and they cover a pretty wild range of possibilities. We're going to try to explore them all and hopefully shed some light on this cosmic mystery.
Without getting, too lost in the weeds.
Exactly. So no equations or anything.
Right. We want to keep it accessible, but there are some really mind-bending concepts we need to dive into.
Okay. Well, are you ready to get started?
Absolutely. Let's do it.
All right. So let's kick things off with something that sounds a bit like science fiction, but it's actually rooted in some really solid physics.
Okay. I'm intrigued.
It's all about quantum fluctuations and vacuum energy.
Oh, now we're talking. Those are some of my favorite things to ponder.
Right. So the basic idea here is that at the tiniest level, like the level of fundamental particles, energy can just appear and disappear.
Yeah, spontaneously. It's almost as if the universe is allowed to borrow energy for very short periods.
Borrow energy.
Yeah, kind of. It has to do with the Heisenberg uncertainty principle, which basically says we can't know certain pairs of properties, like a particle's energy and the time it has that energy, with perfect accuracy at the same time.
It's like the more precisely we know one, the less we can know about the other.
Exactly. And this inherent fuzziness, this uncertainty at the quantum level, allows for these temporary, violations of energy conservation. Those are the quantum fluctuations we're talking about.
So these aren't just theoretical quirks, they have real consequences.
Oh, absolutely. They're not just mathematical artifacts. They have measurable effects.
I'm trying to wrap my head around the implications here. Does this mean the universe could have popped into existence from one of these fluctuations?
That's one of the leading ideas, yeah. It's a concept that really stretches our everyday intuition.
For sure.
But if these tiny energy fluctuations can happen all the time, then why not a really big one?
That's wild.
It is, isn't it? The idea is that the universe might have just materialized out of thin air thanks to this inherent uncertainty at the quantum level.
Okay, and this brings us to the even more mind-bending idea of vacuum energy.
Right. This is where it gets really interesting.
So when we picture a perfect vacuum, we think of completely empty space, right?
Right. A void, nothing there.
But quantum field theory tells us something completely different.
Yeah, it says that even in a vacuum, there's this underlying sea of energy.
A sea of energy.
That's the idea. It's not empty at all. There are these quantum fields constantly fluctuating, creating and destroying virtual particles.
Virtual particles.
They pop in and out of existence so quickly that we can't directly observe them.
How quickly are we talking?
We're talking fractions of a second, incredibly short lifespans.
Wow, okay. But even though they're so fleeting, they still have an effect.
Yeah, they do. The Casimir effect is a really cool example of this. Have you heard of it?
I have, but I'm not sure I fully understand it.
Basically, if you put two uncharged metal plates really close together in a vacuum, there's this tiny force that pulls them together.
And this force is caused by...
the virtual particles. They're popping in and out of existence all around the plates, but the space between the plates limits the kinds of virtual particles that can exist there.
Oh, I see. So there are fewer fluctuations between the plates than outside them.
Right, and this difference in fluctuations creates a pressure difference, and that pressure pushes the plates together.
That's amazing. So we can actually measure the effect of these virtual particles.
Exactly. It's a direct demonstration that even empty space has energy.
Okay, so back to the Big Bang. If these tiny energy fluctuations happen all the time, could it be that the entire universe came from one massive fluctuation?
Well, that's what some physicists have proposed.
Seriously?
Yeah. The idea is that if quantum fluctuations can create these pairs of virtual particles, there's a chance, however tiny, that a fluctuation could be big enough to create a whole universe.
It's like winning the cosmic lottery.
Yeah, something like that. It's a pretty radical idea, right?
Absolutely. But are there any physicists who actually support this idea?
Oh, yeah. Edward Tryon, for example, he was one of the first to suggest this.
What did he say exactly?
He said, our universe is basically a quantum fluctuation that, for some reason, didn't just collapse back into the vacuum.
Like a bubble that just keeps expanding.
A very, very special bubble.
That's incredible. But how do we get from this tiny fluctuation to the vast universe we see today?
That's where the theory of inflationary cosmology comes in. It's the idea that the universe underwent a period of super fast expansion in the first fraction of a second after the Big Bang.
So these quantum fluctuations got stretched out to like cosmic proportions.
Exactly. They became the seeds for the galaxies and all the large-scale structures we see today.
Wow, so these tiny quantum jitters might be responsible for everything around us.
It's pretty wild, isn't it?
It really is. But how do those tiny fluctuations actually grow into galaxies and stars and planets?
Okay, so imagine a balloon with a tiny wrinkle on its surface.
Okay, I'm picturing it.
Now inflate the balloon. What happens to the wrinkle?
Gets way bigger.
Exactly. Inflation basically stretched out these initial quantum wrinkles, making them large enough to become the seeds of galaxies and clusters of galaxies.
It's kind of mind-boggling to think about, but I think I'm starting to get it.
And to add to that, Stephen Hawking, in his work on black holes, showed that these vacuum fluctuations are really important near the event horizon.
The point of no return.
Right. And he found that black holes can actually radiate energy because of these quantum effects.
Black holes can radiate energy.
Yep. It's called Hawking radiation.
Yeah.
And it's all because of these virtual particles popping in and out near the event horizon.
So even the most extreme objects in the universe are influenced by these tiny quantum fluctuations.
It seems that way. And the fact that black holes can radiate energy like this hints that similar principles might have been at play in the very early universe.
Okay, that's incredible. But before we get too lost in black holes, let's move on to another really interesting idea.
All right, what's next?
This one is called the zero-energy universe hypothesis. And well, it's pretty mind-blowing.
Okay, I'm always up for a mind-blowing hypothesis. Lay it on me.
The basic idea is that the total energy of the entire universe might actually be zero.
Zero. How is that even possible?
Well, it sounds counterintuitive, but it all comes down to considering all forms of energy, including something called negative energy.
Negative energy. I think I need a little more explanation on that one.
Right. It sounds a little weird. So think about gravity. It's an attractive force.
Yeah, it pulls things together.
So to pull two objects apart, you have to work against gravity.
You have to put energy into the system.
Exactly.
Yeah.
And that energy is stored in the gravitational field between the objects.
Okay, so it's like the field itself has energy.
Right. And that energy is considered negative because you have to add energy to overcome it.
Ah, I see. So gravity is like a kind of energy debt.
Yeah, that's a good way to think about it. And in cosmology, this negative gravitational energy is thought to be spread throughout the entire fabric of space-time.
So the universe is kind of like a giant energy balancing act.
Exactly. The positive energy of all the matter and radiation is perfectly balanced by the negative energy of gravity.
And this was proposed by...
Edward Tryon, back in 1973.
Wow, he was really ahead of his time.
So if the total energy of the universe is zero, it means the universe could have come into existence without actually needing any energy to get started.
That's right. It's kind of like having a bank account with a zero balance.
Yeah.
You can have credits and debits, but they always cancel each other out.
It's a great analogy.
And because the total energy is zero, it doesn't require an external energy source. It just, like, exists.
So we're back to the idea of something coming from nothing.
In a way, yes, but nothing in this context is a very specific kind of nothing. It's a state where all the different forms of energy balance out perfectly.
All right, and how does the expansion of the universe fit into this zero energy picture?
Well, as the universe expands, more matter and radiation come into being.
Right, stars are born, galaxies form, etc.
But at the same time, the gravitational field gets weaker, so the negative energy also increases.
So it's like the expansion itself is maintaining this energy balance.
Exactly. It's a pretty neat concept, right?
It really is. And it's amazing how these ideas from cosmology and quantum mechanics all seem to connect.
Definitely. And, Stephen Hawking explored similar ideas, suggesting that the universe could have originated from a quantum fluctuation in a vacuum state, which aligns with the zero-energy concept.
So Hawking was on board with this too.
Oh, yeah.
Yeah.
He even incorporated it into his work on the Big Bang and black holes.
I guess when you're dealing with the origins of the universe, you have to be open to some pretty wild ideas.
Absolutely. And speaking of wild ideas, let's talk about cyclic or eternal universe models.
Now we're getting into some truly mind-bending territory.
I love these models. They really challenge our assumptions about the beginning and end of the universe.
So instead of a single Big Bang, these models suggest the universe might go through cycles of expansion and contraction or even exist forever.
Right. And they try to answer some of the questions that the standard Big Bang theory leaves unanswered, like what caused the Big Bang?
And what happened before it?
Exactly. So the first model in this category is the oscillating universe model. It was considered by Einstein and later developed by Richard Tolman.
Okay, and what's the basic idea there?
The idea is that the universe expands to a certain point, then gravity pulls everything back in, causing a big crunch.
A big crunch, like the opposite of the Big Bang.
Right, and then this big crunch somehow triggers another big bang, and the cycle starts all over again.
So it's like a cosmic heartbeat, expanding and contracting forever.
Yeah, that's a good way to put it. But this model has some problems. One big issue is the concept of entropy.
Entropy, that's like a measure of disorder, right?
Exactly. And the second law of thermodynamics says that the total entropy in a closed system, like the universe, always increases over time.
So things get messier and more chaotic as time goes on.
Right. And if each cycle of expansion and contraction generates more entropy, then future cycles would be longer and more spread out.
So going back in time, the cycles would get shorter and denser.
Exactly. And that makes it hard to imagine an infinite past with endless cycles.
It's like trying to rewind a broken record.
Yeah, the analogy works. Plus, there's the whole issue of dark energy and the accelerating expansion of the universe.
Right, if the universe is expanding faster and faster, it's unlikely to collapse back in on itself.
Exactly. So the oscillating universe model has some serious challenges to overcome.
Okay, so what's another model in this category?
Well, there's conformal cyclic cosmology, or CCC for short, proposed by Roger Penrose.
And this one is different because,
It involves infinite cycles of expansion but no contraction. Each cycle ends in a state called heat death.
heat death. That sounds a bit grim.
Well, it's not exactly a party. Basically, it's a state where all the stars have burned out, black holes have evaporated, and everything is incredibly spread out and cold.
So the universe becomes like a vast, empty wasteland.
Pretty much. But here's the twist. Penrose argues that this state of maximum entropy, this heat death, is mathematically equivalent to the conditions of a new Big Bang.
What? How is that possible?
It's a little complex, but it has to do with the way space and time are connected and how they behave at extremely high energies. The idea is that at these extremes, the scale of the universe becomes irrelevant.
So the huge, empty universe of heat death becomes the seed for a new, tiny, dense universe.
Exactly. It's like a cosmic reset button.
That's wild.
Yeah.
And does this model have any observational support?
Well, Penrose claims to have found patterns in the cosmic microwave background radiation that are remnants of black holes from previous cycles.
Wow, that's a bold claim. But it's still pretty controversial, right?
Oh, absolutely. Most cosmologists are skeptical about it. But it's definitely a fascinating idea.
Okay, on to the next model. What's up next?
All right, this one is called the ekpyrotic universe model, developed by Paul Steinhardt and Neil Turok. And this one brings in the idea of extra dimensions and brains.
Extra dimensions,
Right.
like from string theory.
Yes, exactly. So imagine our universe as a three-dimensional brain floating in a higher dimensional space.
A brain, like a membrane.
Yeah, think of it like a sheet of paper. Our universe is everything on that sheet, and there could be other brains out there, other universes floating parallel to ours.
Okay, so other universes would be like other sheets of paper.
Right. And in the ekpyrotic model, the Big Bang is caused by a collision between our brain and another brain.
So like two sheets of paper slamming together.
Exactly. And the energy of that collision creates the matter and radiation that fills our universe.
That's an awesome visual.
Mhm.
So what are the benefits of this model?
Well, for one thing, it avoids the entropy problem we talked about earlier, because each collision effectively resets the entropy of the universe.
So it's like starting with a fresh sheet of paper each time.
Yep. And it also provides a potential explanation for the large-scale structure of the universe, like the distribution of galaxies.
How so?
Well, the patterns of energy and density created by the collision could have acted as seeds for the formation of galaxies and clusters of galaxies.
So the structure of the universe is like a cosmic fingerprint of this ancient brain collision.
That's the idea.
This is all so fascinating. All right, I'm ready for the last model in this category.
Okay, this one is called the quantum bounce model. It comes from loop quantum gravity, which is a theory that tries to combine quantum mechanics and general relativity.
So it's a theory of quantum gravity.
Exactly. And in loop quantum gravity, space-time isn't smooth and continuous. It's made up of tiny, discrete chunks.
Like pixels on a screen.
Kinda, yeah. And these chunks have a minimum size, so they prevent the universe from collapsing into a singularity.
So no singularity at the Big Bang.
Right. Instead, the universe contracts to a certain point, then these quantum effects cause it to bounce back into expansion.
So the universe is always expanding and contracting, but it never quite reaches a singularity.
Exactly. It's a perpetual cycle of bounces.
And has this model been proven?
Well, it's still very theoretical. There's no direct observational evidence for it yet, but it's a really interesting possibility.
All right, so we've explored models where the universe keeps cycling, but what about the idea of multiple universes?
Ah, the multiverse. Now we're really getting into mind-bending territory.
Right, so the basic idea here is that our universe is not the only one. It's just one of many.
And these other universes might have different laws of physics, different histories, even different
Yeah,
dimensions.
I need to sit down for this one. This is a lot to take in.
It is, isn't it? But the concept of the multiverse is actually a pretty natural consequence of some of our best theories in physics.
Like,
Well, for example, the theory of inflation, which we talked about earlier, suggests that there might be regions of space that are still inflating, creating new universes all the time.
so our universe is just one bubble in a much larger, eternally inflating multiverse.
That's one possibility, yes.
And string theory also supports the idea of a multiverse.
Yeah, string theory allows for a huge number of possible universes, each with its own set of physical laws and constants.
It's like a cosmic menu with infinite options.
Exactly. And then there's the many worlds interpretation of quantum
Oh
mechanics.
yeah, the one where every quantum measurement creates a new universe.
That's the one. So every time a particle can be in multiple states, reality splits, and each possibility plays out in a separate universe.
So there's a universe where I had cereal for breakfast instead of toast.
And another where you had both, and another where you skipped breakfast entirely. The possibilities are endless.
That's a little overwhelming,
Right.
but also kind of cool.
Right. It's a very different way of thinking about reality, but it's a very logical consequence of the mathematics of quantum mechanics.
Our sources also mention Max Tegmark's classification of the multiverse into 4 levels. Can we go over those?
Absolutely. So, level one is the easiest to understand. It's basically the idea we just talked about, that inflation creates an infinite number of bubble universes.
Okay, so like different rooms in a giant cosmic house.
Exactly. And these universes would all have the same basic laws of physics, but they might have different initial conditions leading to different histories.
So some universes might have more galaxies than others, or maybe life evolves differently.
Exactly. It's all about the different ways those initial quantum fluctuations could have played out.
All right, what about level 2?
Level two is where things get really wild. This is the multiverse of string theory, where different universes can have completely different physical laws.
So gravity might be stronger or weaker in some universes.
Right. And the speed of light could be different, or the masses of particles could be different.
So like some universes might be governed by laws of physics that we can't even imagine.
Exactly. It's a pretty mind-blowing concept.
All right, what about level 3?
Level three is the many worlds interpretation we talked about earlier. Every quantum measurement splits reality into new branches, creating a vast network of parallel universes.
So like a cosmic tree with infinite branches.
That's a good way to picture it. And each branch represents a different possible outcome of every quantum event.
So there's a universe out there where dinosaurs never went extinct.
And one where humans never evolved at all. It's a pretty dizzying concept.
It is, but I'm saving the best for last. What about level 4?
Level four is the most abstract and perhaps the most controversial. It's called the mathematical universe hypothesis, and it was proposed by Max Tegmark.
Okay, and what's that one all about?
Basically, it says that all mathematically possible universes actually exist.
So any universe that can be described by a set of consistent mathematical equations actually exists somewhere.
Exactly. It's like saying that mathematics isn't just a tool for describing reality, it is reality.
Wow, that's pretty profound, but also very hard to wrap your head around.
It is, isn't it? It takes the idea of the multiverse to its most extreme conclusion.
So there's a universe out there where pi is actually 3.
Maybe. Or maybe pi is still pi, but the other laws of physics are completely different. We really have no way of knowing.
Okay, so we've talked about multiple universes, but where do higher dimensions fit into all of this?
Well, in some multiverse models, like those based on string theory, higher dimensions play a crucial role. String theory requires at least 10 dimensions to work mathematically, and these extra dimensions are thought to be curled up very small so we don't experience them directly.
So like a garden hose that looks one-dimensional from far away, But up close, you can see it has a circumference.
Exactly. The extra dimensions are like that circumference, just curled up at incredibly tiny scales.
And these extra dimensions could be where other universes exist.
That's one possibility. In brain cosmology, for example, our universe is a three-dimensional brain embedded in a higher dimensional space, and other brains, other universes, could be floating around out there.
So collisions between brains could be what causes Big Bangs.
Exactly. It's a pretty wild idea.
It is. All right, so we've covered a lot of ground here, but there's one more possibility we need to address.
Okay, what's that?
The possibility that maybe, just maybe, we don't have all the answers yet. That maybe there are unknown laws of physics that we haven't discovered.
Right. It's humbling to think about, but our current understanding of the universe is almost certainly incomplete.
Like we have quantum mechanics and general relativity, which are both incredibly successful theories, but they don't always play well together.
Yeah, especially when we're dealing with extreme conditions like the Big Bang or the center of a black hole.
So there might be a deeper theory, a theory of quantum gravity that unites these two giants.
That's what many physicists believe. And there are several candidate theories out there, like string theory and loop quantum gravity.
What about dark matter and dark energy? Could there be evidence of unknown laws of physics?
Absolutely. We know so little about them, and they make up the vast majority of the universe's energy.
So it's like we're missing a huge piece of the puzzle.
Exactly. And until we figure out what dark matter and dark energy are, it's hard to say for sure where all the energy in the universe came from.
And what about the arrow of time? Why does time seem to flow only in one direction? Is that also related to unknown laws of physics?
That's another big mystery. The second law of thermodynamics explains why disorder increases over time, but it doesn't tell us why time has a direction in the first place.
So maybe there are deeper laws of physics that govern the nature of time itself.
Maybe. It's all very speculative at this point, but it's definitely something that physicists are thinking about.
Wow, this has been an incredible journey. We've explored so many mind-blowing possibilities from
Yeah.
quantum fluctuations to the multiverse and everything in between.
It's amazing how much we've learned about the universe, but it's also amazing how much we still don't know.
So to wrap things up, where do we stand on the question of where all the energy in the universe came from?
Well, we've seen that there are a lot of compelling ideas out there, but there's no single definitive answer yet.
It's still an open question.
Oh, absolutely. It's one of the biggest mysteries in physics.
So what do you think is the most promising avenue for future research?
Well, I think finding a theory of quantum gravity is key. If we can understand how gravity works at the quantum level, it might give us some clues about the very earliest moments of the universe.
And maybe about the origin of energy itself.
Exactly. And we need to learn more about dark matter and dark energy. They might be the key to unlocking a whole new understanding of physics.
So there's still a lot of work to be done.
Yeah, but that's what makes it so exciting. We're still at the very beginning of our quest to understand the universe.
Well, I don't know about you, but I'm feeling a little overwhelmed by all this cosmic awesomeness.
Me too. It's a lot to take in, but it's also incredibly inspiring.
So for all you listeners out there, what do you think? What resonated with you the most? What questions are still swirling around in your mind?
Yeah, what possibilities have really captured your imagination?
And what do you think the future holds for our understanding of the universe and its origins?
Keep those cosmic ponderings going, because the more we explore, the more incredible the universe becomes.
Thanks for joining us on this deep dive into the mystery of where all the energy in the universe came from. Until next time, keep looking up and keep asking those big questions.
We'll see you next time.